All right, so today we are dealing with the spectral properties of the Laplacian operator. So last time we computed explicitly the eigenvalues on the square of the Laplacian with Neuman boundary conditions. And today we are going to see how to generalize this thing for open bounded set with a boundary which is regular. So what we are going to do today, as I said, is we are in fact dealing with this problem. So we will use the L2 setting, and so we'll use this notation. This H here will denote L2, and this V here will denote the Sobolev space H1. Right. So you're familiar. I assume that you are all familiar with the LP spaces and the classical Sobolev spaces. So the H1 is is included in L2, and when you take the derivative in the sense of the distributions, then you have a then the distributions are in L2 also. Okay, so that's so we're dealing with that in detail today. So the question is, can you guess some eigenvalue for our problem? So I repeat, can you find an eigenvalue for our problem? Yeah, no problem. Yes, welcome. So can you see an eigenvalue here? So I look for a number, real or complex, such that when I take the Laplacian of the function, so u is a function defined on my domain omega, and I want that when I take the Laplacian of this function is the same as taking the function, multiplying it by lambda, and I have the same result for all x on omega. And furthermore, I want that when I take the gradient of u, and this point here is the scalar product in we're working on Rn, this is 0. Well, so yeah, there's an easy one. There's an easy eigenvalue. It's 0, right? So if you take lambda equals 0, it works with. So I need, and what is the function? And you take u constant. So if u is constant, then when you take the derivatives of u, this will be 0. and this is 0 and this is 0. So when u is constant, any constant function u is an eigenfunction of my problem with the associated eigenvalue 0. So I will write now lambda node equals 0 and u0. So we like to have that the integral of u0 on omega is 1. So I would like that u0 square is 1. So I can just take so this gives me that u0 square equals 1 divided by the integral over omega, and I take u0 to be the square root of that. Oops. Okay, so just to have that the integral of u0 square is 1. All right. Okay, so I found one eigenvalue. That's good. Can we find other eigenvalues? Yes, the answer is yes. But so now we need something more elaborate. So can we find other eigenvalues? So we will go through a process. So let's try to find another one, lambda 1. So let's define lambda 1. So our lambda 1 will be a real number, and it will be defined by, I take the inf so of this quantity, the integral of omega of so let's write it this way. I'm going to write that this way. So I'm going to let you know what's that. So here, this is defined as, I said that I work on R to the N. So this is okay. This is my definition of the grad of u to the square, right? And so I'm looking at this infimum not for every function. So first I need to define where I work. So I will work here. So I will work in H1. So H1, I said that I use the notation V. Okay. And furthermore, I will work on the space which is orthogonal to the space of constant functions. So I impose also that integral of u is 0. So it's orthogonal when I choose my scalar product to be the scalar product on L2, right? So everything is important here, but let's focus on this thing. So I work on V, so it's H1, so these things are well defined. And this integral is well defined as well. So I look at the functions that are of an integral 0, and I forgot something here. Furthermore, I want that the norm of u in L2 is 1, okay? Where also, by definition, we have that. Okay, so this number is well defined, okay? Because it's an infimum, this quantity is a positive number, and okay, so this is well defined, and I can find a sequence of so let us write that. I will write that. So H1 here, I will write that H1 is the set of the function in V such that the norm of u of in L2 is 1, and the integral over u is 0. So so I can find a sequence by definition of lambda 1. I can find a sequence a sequence of functions un such that lambda 1 is the limit of this quantity. Okay, that's by definition of the inf. All right. So is everything okay up to this point? So what we have next? So so we have a sequence here in this space H1. So here you can see that so this will be bounded. Every function that converges is bounded. So this is bounded. Also, the norm in UK in in L2 is 1. So in fact, my sequence of functions UK are bounded in V, which is my Sobolev space. So then, therefore, my sequence UN is bounded in V. So, but we have the Relish theorem, which says that the suborder space H1 is compactly embedded in L2. Okay, so from the Relish theorem, we deduce that there exists a subsequence of UN which converges to a function phi1 in L2. So in L2, but my L2, I wrote it as H. Yeah, so because I wrote here phi node, but yeah, we will call it phi node. Okay. So here, let's call it phi node. All right, and so I call this is a subsequence of UN, but I call it again UN to avoid any unnecessary heavy scripts. So we have therefore that UN converges to phi1 in H. So H is L2. Okay. So but UN equals 1. So is the norm of phi1. All right. So so what we would like to have is that so I recall that lambda 1 is the limit as k goes to infinity of so sorry, it's that but UK, so now is a subsequence, but UK converges to some phi1 in L2. Yeah, so what I would like is that I would like to have that grade UK converges to gradient of phi1, but I don't know about that. Is there exists or I don't know. Okay, so can we define that? So in order to see that this thing is well defined, we need to prove that, in fact, UK, this is converging. So what I would like to do is to prove that in fact, my sequence UK is Cauchy in V. If this is the case, then it will be good. All right, but in order to prove that, so let's look at some. Let's look at this quantity. So the difference of UK and UL in L2, I don't have a problem because I know that the sequence is converging, but I need an estimate on that. So this is a big question. Can you prove that this is as small as you want when K and L are large as you want? So next, so we want to prove that this is small when K and L are large. So let's look at that more in detail. So first, let us remark that so this norm is the norm associated with the product scalar. That I let you verify that. So what do I obtain here? So I will obtain 2 I will obtain that. Okay. Because this norm is associated with a product scalar. So you will have a scalar product of grad UK, grad UL, and then minus grad UK, grad UL. So things will cancel out, but you will remain with these things. Okay. So I let you do the details of it. All right. So I want an estimate on that. So from here, I get that grad UK minus grad UL square equals 2 grad UK square plus 2 grad UL square minus grad UK plus grad UL square. All right, so first things first, this converges, right? This is the definition of my lambda 1. So this is converging to lambda 1. And this is converging also toward lambda 1. All right, so when K and L is large enough, this will be close to 4 lambda 1. What about this term? Well, what I do know is that okay, because since lambda 1 is a nymph, I know that if I look at square, but I want, if I take this, so So here it's the norm in L2, it's inside. This is true by definition of lambda 1. Because this function here, because UK plus UM divided by the norm in L2 of UK plus UM, you can check that this belongs to my space H1. That this is not the Sobolev space. It's H1. It's included in V, but just don't confuse the H subscript 1 with my Sobolev space H1, which I denoted by V. All right, so here the important point is the following, is that therefore, from that, I deduce that UN plus UM square times lambda 1 is less than this. Okay, and yeah, I want to estimate that here. So if I multiply by minus, I will get minus, and I will change that. So so finally, I have that minus, sorry, minus is less than lambda 1 So let's write the whole inequality. We have that grade UN minus grade, I changed the L and K by N and M. Let's go back to the K and L. K L is less than 2 grad UK, so it's 2 grad UL to the square minus lambda 1 UK plus UL square. Okay, so I know the limit of these ones. What about these ones? Do you know what's the limit of this thing? Actually, this will be as close as 4 as I want if K and L as large enough. So why? So why UK plus UL square. So this is exactly the product scalar in L2. So this will be UK square plus UL square plus 2, and here it's the integral UK UL. This converges, this is equal to 1 by construction. And this here, let's do the details. If I look at UK UL, this is going to converge to 1 when K and L is large enough. Why? Because if I, for example, do that, this is 1 actually, but this is equal to right? And so therefore it's less than the norm of UK times the norm of UL minus UK. But I know that the sequence converges in L2. So this is as close as 0 as I want. So finally, this is 1. Finally, I know that that this is as close as I want of 2. So finally, this whole term is as close as I want of 4. Okay, so at the end of the day, you have 2 plus 2, 2 lambda 1 plus 2 lambda 1 minus lambda 1, 2 times 4. So this is as close as I want of 0. So this now, so therefore, therefore, is a Cauchy sequence. So so it converges. So now, so you have that the grad of UK converges toward some function in L2. But since UK converges to phi 1, this is a classical thing with distributions. You don't have a choice. It means that, in fact, grad UK converges to grad of phi 1. But finally, what do we have? We have that lambda 1 is equal to this quantity. And you have also that with phi 1 equals 1. All right.